Thanks for joining this online seminar. Good afternoon, everyone. My name is Yunjia Wu. I'm an associate professor at the Department of Hydraulic and Ocean Engineering at National Cheng Kung University in China. So today we are very honored and happy to invite Professor Philip Liu to give this seminar, which will be talking about tsunami. Professor Philip Liu is a famous researcher in the area of coastal engineering. So Professor Philip Liu is the Professor Emeritus at the Cornell University, and currently is the Distinguished Visiting Chair Professor at National Cheng Kung University in Taiwan, which is supported by the Yushan Fellow Program of the Ministry of Education in Taiwan. So this is the reason that we have this chance to invite Professor Philip Liu to give a talk. And as you know, Professor Liu has received many academic awards, such as a Fellow of AGU and the member of the National Academy of Engineering and an academician of the Academic Syndicat in Taiwan. So Professor Liu's research has a very high impact. For example, one of the numerical models that he developed, that's a CAMCA model, is the first attempt in the world to simulate the tsunami from generation, propagation, and inundation inland. And this model has been employed in many countries in developing the tsunami warning system and inundation map, as well as the tsunami hazard assessment. So the topic of Prof. Liu's talk today is also related to tsunami, which is the non-stationary probabilistic tsunami hazard assessment incorporating tide and the sea level rise. This is probably a new framework to perform the PTHA. So I think now is the time for you, Prof. Liu. Thanks.
First of all, thank you very much, Yunda, for your introduction, and also for your the committee's invitation to give this seminars. And so today, I would like to talk about different ways to perform the tsunami hazard assessments. All right, so as I said, so this is the first slides, right? I'd like to talk about different way of performing tsunami hazard assessments. In particular, now we are worried about the climate change induced sea level rise, and how do we include that kind of a long-term effect, longer times effects on the tsunami hazard assessment. In fact, you can ask general questions, and when you think about assessing different kind of hazards, then how do you incorporate this kind of longer term type of background informations on those kind of phenomenon? Showing here is all my co-workers and for this particular talk, and they include my former PhD students, Ignatius and Patos, and the first one, the last one. And those both are Chileans, and so they are the experts actually on some of the actual tsunami events happening in Chile and other places. Then I have my colleagues from Cornell University, Professor Gregorio. He's a expert in stochastic processing, and also then Jennifer is a professor in the Scripps Institute. So this is a collaboration among many faculty, many researchers who has a different kind of background, which is really needed when we study this kind of problems. All right. As Yunda mentioned that currently I'm stationed at the National Cheng Kung University in Taiwan, but we're going to go back to Cornell pretty soon. All right. So let's see. Tsunami happens often enough to get some attentions. And in particular, along the so-called Pacific Rim of fires has had many different tsunamis happen in the history. One of the most recent large tsunami, which has a significant impact, you probably remember, is 2011. The tsunami happened on the east coast of Japan near Tohoku, Sendai area, and that caused a large tsunamis and actually damaged nuclear power plant nearby, and it caused significant effects, long-term effects. Now, most recently, actually, just last January of this year's, there was another earthquake in the order magnitude of roughly 7 or 7.5, and also that's on the west coast of Japan, which is facing Japan Sea, and that earthquake very near shore also generates tsunami and causes some damages in the local area. This figure here shows the what kind of a different degree of tsunami warning messages sent out during and after the earthquakes. And so epicenter is already right here, and you can see that different color codes implies that the relative significance of these expected the different damages caused by the tsunami. So anyway, so it's important, all right, in some sense that be able to have a quantitative type of assessments of the possible tsunami damages in different location once the earthquake or tsunami occur. But also it's more important for the longer term planning, coastal planning purpose is looking into the future to have some sort of assessments on what degree, what kind of damage is expected if and when certain earthquake or tsunami occur at certain locations. So this is what we're talking about, all right? Tsunami hazard assessments. Now, besides the Japan, in the neighborhood, in the vicinity of Taiwan's and or in the larger sense in the whole South China Seas, there's another very high potential earthquake or tsunami zone, generating zone. That's the Luzon or the Manila Trench. In the case here is between Taiwan, Manila, Philippines, and this trench has a great potential to rupture sometimes in the near futures, and that might cause generate large tsunamis, and that can generate tsunami large enough that propagates to the south, west of China, Taiwan, and also into the southern part of China and Hong Kong's and Zhuhai areas. All right, so this is a simulation of the particular event, a magnitude of very large 9 that happened on the segments of the Manila Trench, and you can see the wave will propagates reach Taiwan roughly in the order magnitude over 3 hours, right? So we're going to visit some of these this particular possible events later on. Just give you some sense of degrees of damage could be caused, or kind of a tsunami flooding can be a cause. All right, so what do we usually do if we need to assess the tsunami hazards? Then typically, in the more traditional ways, and the tsunami hazards are done by the so-called using numerical models, and to determine the tsunami inundations or tsunami highs in certain coastal area in a very deterministic way. That simply means that if you can specify the worst case scenario of a particular earthquake that is tsunami-genic, that means that these kind of earthquake can generate tsunami. Then you gather all the parameters and for due to coming from the earthquake, and use that as an input to generate the tsunami locally from the source region, then somehow propagates this wave from the source region. Sorry. All right. From the source region to the target, the coastal region, then you need a numerical model. That's what we're talking about, tsunami models. Now, Yunda mentioned in the introductions that typically the tsunami is a very long wave in the very shallow water. So the governing equation from the fluid mechanics, hydrodynamics point of view is simply so-called shallow water wave equation. Then we have some kind of model called COMCOT, which you can do a reasonable job in most of the situations. Then the outcome of this is the inundation water depths, including the water levels and also the current velocity, which might be very important when you're trying to understand the impact of tsunami on some coastal structures. So it's not just a water level or wave height, but also the momentum fluxes that is the current related to the velocity field. So that's for in the particular targeted regions. So this is totally deterministic. That means that if you can estimate, you can somehow figure out what is the worst case scenario, what is the largest earthquake could happen, say, in the Manila Trench. And also you could figure out what is the distribution of the fault plan distributions. And then you can assumes that the model you're going to use, the tsunami model you use, are accurate enough, then you can estimate what is the results, including the velocity and the water depths. Okay, so there's a lot of assumptions in there in terms of certainties of these parameters that in reality, everywhere, everything I have spoken here contains a high degree of uncertainty. You know, we cannot really 100% sure what are the earthquake parameters in the future, especially, and we cannot even for sure what is the bathymetry looks like, say 100 years from now, 50 years from now, right? So at the best, we have some survey data right now. Even those data are still not very certain, but let alone say 10, 100 years from now. And a lot of things could change into the ways that we cannot really predict. And so those are the open questions and uncertainties that we should take into considerations when we do the so-called hazard assessments, all right? So quick summary up to now is that so people have done this kind of a hazard assessment, a tsunami assessment in this particular talk, and using the deterministic approach, in particular looking at the so-called worst case scenario, right? Assuming everything is 100% certain, then you can say this is the worst case situation, then this is the worst case outcome, and so-called worst case outcome that will be includes the distribution of flooding water depths in certain area and also the velocity distributions that in terms can be used to estimate the damage might be caused in the local locals and in terms of the damage to the structures, so on and so forth. Okay, so but in reality, people realize that more and more, especially when you think about longer term kind of assessments, right? You're talking about what happened, return periods 100 years or even longer, 400 years, and are we sure everything is certain? How do we actually propose absolutely sure what is the worst case scenario? So it's a lot more realistic than start to think about introducing the probabilistic approach. And then basically, it means that you want to consider all the uncertainties involved in the input parameter, including the process, even the model equation has certain uncertainties. And then what is the results? Then we'll propagate these uncertainties from the source region through the model or some other mechanisms to the target region. Then from that, then you can construct the probability of certain damage or certain water level can happen within certain period of time, right? Time frame you design. So that is the so-called probabilistic approach. But for a long time, that kind of a probabilistic approach people are using, including myself, is assume that the uncertainty, the probabilistic distributions, it obeys some kind so-called stationary process. And that simply means that it's not going to change whether you think about 50 years from now, the probabilistic distribution, or 100 years from now, right? It was a stationary process, to be simply said. And now, of course, that is a simplification in a lot of kind of different hazards. Longer time effects is important. So, for example, in our coastal problem, right, and we're thinking about what is the effects of climate change, right? So what is the impact of climate change as far as we're concerned here? That's in terms of sea level rise. Though sea level rise gradually, few centimeters, all right, per years or less than centimeter. And then what happened is that becomes important after if you consider the hazard events, the return period is 100 years, 50 years, 100 years, or even longer. Then, so that depends when does that occur, then this will actually have a different kind of background water depth, right? And so that is one scenario. Then you have to think about this probabilistic approach is no longer stationary, is non-stationary process. Then even for the shorter term type of problem, a time scale problem, like a tidal range, right? So tidal fluctuation. So if tsunami happen at a certain hour, there's a high tide versus there's a low tide at the different hours, and that could have a different kind of consequences, right? So even that, you probably have to think about it depending on what is the objective of your work. So basically, this is what I'm going to talk about in a very, very high level. There's a lot of technical details. I don't think I can actually do that with a very short period of time. Fortunately, there are some publications I can give to you here. These are the papers, all primarily done by the first author, Ignacio. The first two papers basically are his PhD thesis work. Then we extended it to consider non-stationary process after he became a postdoc at Scripps and also working with me for a while as a postdoc. So, so these are the papers. The first two papers basically is a stationary process and just looking at how do you propagate uncertainties of earthquake parameters and through the equations like COMCA or shallow water equations into the target coastal region, and then look at the probabilistic results of the flooding. And then later on, we start to think about the non-stationary approach and how do we incorporate, for example, the sea level rise and the tidal fluctuation, so on and so forth. So they're all here. There are lots of detail in there. If you're really interested in detail, please take a look at it, and you can get it very, very easily. Okay, so let me, I know I don't have too much time here, but let me go very quickly to talk about the so-called stationary type of the probabilistic assessment approach, right? The simplest that put it in the more in the layman type of kind of presentations. And basically, there are several steps we need to take, right? Basically, we're taking this as a stochastic approach, right? So basically, the the uncertainties in the source region, that in this case is really earthquake, the tsunami-genic type of earthquake, right? By the way, there are kind of earthquake that will not generate tsunami. So we are really talking about we are talking about type of earthquake that will generate tsunami, but what generates tsunami is because the rupture of the fault plane and cause the displacement of the sea floor. And so you will have to input the parameters for the fault plane parameters, displacement of the fault plane. Okay. And now we treat that as a random the random fields, right? Slip distribution is a random field. Then also the location of the epicenter is also important. That is also considered the random vector, though they are not totally random, because we do know the geophysics, the geological of a fault plane. We know the location that is constrained in the world. It's not really can happen anywhere. Now, if we need to specify what is the probabilistic characteristic of these parameters. Now, how do you do that? Basically, it's based on the historical informations. Then you're trying to construct the probabilistic distribution of these, for example, the slip mechanisms. All right. Then the next thing is that really trying to do the sample, and what you want to do is that you use that as an input for the so-called tsunami model equations, and propagates in these random field through the equation, through the tsunami equations, or through the shallow water wave equation. That is a deterministic equation. All right, the input is random, and through deterministic equations, then you come out with it's a random field again, which is output, as I said, is the inundation depth and velocity, so on and so forth. So you have to somehow to do the sampling of your generations for the input, and find the best way to propagate these the samples of the input data to get your outcome. Okay. Now we in those papers we introduce or discuss a different way of samplings, and also different way of propagating the uncertainties through the governing equation. Now, the most straightforward way of the Monte Carlo's methods that usually requires tens of thousands of samples, and if you think about very large domains of propagation, might becomes very costly. And but we introduced this so-called stochastic reduced order method, and that can actually make the methods the calculation much more efficient, and without sacrificing the accuracy all that much. Right. So that is the work by Ignatius in the thesis, the primary contributions in that sense. Right. So the as I mentioned here, that so the slip distribution here is normal distributions. Right. So it's a stochastic. It's the stationary. Right. So put it a little more precisely, is that so the probability, so in simply says that if you assume it's a stationary process, and with a constant rate lambda I, and if you have a different independent sources, tsunami sources, that means that the subdomain of the ruptures in the entire rupture region, then in the probability of no tsunami events occur within the time frame t, then can be written in this stationary, the exponential function e to the minus lambda I sum t, and and you simply can be writing in this way. Okay, so that I think everybody knows that. Then the issue is what is the lambda t, right? That is based on the historical information for a particular site, the earthquake situations. And then, of course, the longer time is lesser information you'll have, then the estimation of lambda I becomes less accurate. And that's the problem, right? And so so the overall probability of at the downstream end, right, is to get this information saying that the overall probabilities of not exceeding HC. What's the HC? Is some fixed criteria you have, say the inundation water depth, or say 1 meter or 2 meters. Then and if you over this say 100 years or 50 years T, and then mathematically you can write down in this form what's the lambda I and the probability PI, which is saying that for the ith events and the event I, when H is greater than the criteria you set up HC. So these are all the simple statistics, and then you finally can deduce that the likelihood of having one or more event tsunami with intensity greater than HC is simply written in this way. So this is a very traditional way, the so-called stationary, assuming stationary process. Then you come up with through the scaling process, or that you come up with probability P0 here, then through the propagation process, then in the outcomes you can find out what is the end results, right? For the likelihood to have one or more events, tsunami events with the intensity greater than HCs. All right, so that is the stationary stuff. Then later on, I'm going to sort of briefly mention what happens if it's non-stationary, right? So by including, for example, the climate change, seawater level rise or tides, right? And how do you modify this, right? Okay, so this is just a one quick summary. When we apply this probabilistic approach with assumption that this is the stationary process, all right? And so apply to the South China Sea situations, and in particular look at Manila Trench as a possible source of the tsunami generations. And without going really too much into the details, that would take a really tremendous amount of time to look at it carefully. Basically, as I said, there's the Manila Trench actually can have three segments, A, B, and C. They are considered to be unlocked, the fall plans, and they can rupture independently. Then the worst case scenario, obviously, is that when they rupture simultaneously, right? But in this case, that will actually have consider three segments separately, and then for each sequence, you determine this lambda I, and using the historical data. As you can see that all the data will have is up to 7, magnitude 7, and for large magnitude of ruptures is really the ones that were interesting, that we're concerned of, because that's indicates a larger, very large earthquake, magnitude of 9. Then that is all basically based on the extrapolation. Okay, you can challenge, say maybe there's a better way of doing it. Estimate the lambda values. Okay, so then again, then when you are trying to estimate the source regions, that you can then divide it up, the fault plan, the 3 regions, into subdomain. With each domain you assign some kind of different probabilistic characteristics. And now I think here we have 1 to 11th segments or subdomains regions. Then, as I said, very gloss this all over, that you use this probabilistic distribution function, then you do the sampling, then you do the propagation of uncertainties through the shallow water wave frequency compound. Then the output will be the probabilistic distribution of the inundations and the velocity, then you can use the previous slide results and calculate the likelihood of a say when the water depth here inundation depth is greater than specified HC and within 100 years, t equal to 100. So these 6 panels here basically is showing you the results at 2 different particular locations. One is in Kaohsiung, in Taiwan, all right. Another one is rows in Hong Kong areas, all right. And so this is for t equal to 100. And so, for example, in this panel here, basically saying that if the likelihood to have a tsunami that can generate the inundation depth is 1 meter, all right, 10 to the 0 meters here is somewhere is about definitely bigger than 10%, right? Much bigger than 10%. I don't know, 20% or 30%. In this particular location, one in the offshore is offshore of Kaohsiung. All right, so you can actually see that in Hong Kong the probability becomes much more smaller, right, relative to what happened in Kaohsiung. So you can get these kind of informations, and even you change the t value, say from 100 to 200 and or less than 100, then you can get a probabilistic information of the occurrence, certain type of inundation could happen at the different locations, right? So these are the typical type of data results you will get. Now, so our interest, however, is not just that, was asking challenge. Oh, okay. So this kind of analysis doesn't really matter when this tsunami might happen, right? This is 100 years, but you could have, for now, you could have say move from the 200 years from now, measuring from the 100 year from now. So the time duration can change with in the reference time. In other words, there's no sense of history at all, right? Is a stationary process. Basically, there's no memory of what happened, right? Previously. In that sense, is a stationary situation. Now, think about this, that if we actually take the sea level rise effect seriously, then you have to set a time reference now. You have to say, today, sea level rise is, sea level is such, then 100 years from now, the sea level could go up or go down as a different location, then that might have effects of on the tsunami inundations, right? Then you can see that, and then if it happens 50 years or 200 years from now, then the result could have a different impacts. So we like to see whether we can incorporate that, and if what is the best way or easy way to do it, or a big framework so on that. So this is the simple basically the simple idea, right? So in other words, if we consider a time horizon that is a capital T, within this time horizon, that the sea level could change, right? You can think about this a gradual change upward, that will be sea level rise type of scenario. And or you can think about this time zone, it can be actually considered as a tide. So within 24 hours, the tide can go up and down in certain fashions in a certain location. Then what will be the impacts of the tsunami in terms of inundation and also impact, right? Now, naively, you can imagine that, for example, when we talk about the T1, the first time horizon T1s, and the sea level rise and versus the current situation is a little bit up, right? And okay, so so I guess I'm saying that because the different surface elevations and you will have a different kind of outcomes, then let's see what we are going to do about it. Okay, so quickly, quickly running out of time here. So this becomes a so-called non-stationary process, and because you cannot prescribe the probabilistic characteristics independent of the time frames, right? You have to think about time frames. Now, the stationary process, as I mentioned before, is written say that the likelihood of have one or more tsunami with the inundation greater than HC can be written as this e to the minus one minus e to the minus as the summation of orders. And so now the way to think about it is that this probabilistic function here, right, and it's going to actually change in times due to the ZAC position when the events is happening, right? For in the previous slides, you have a T1, T2, T3, T5, and so if you one simple way to think about it is that if you can subdivide M the time period time horizon T capital T into subdomains, say M subdomain with some delta T, right? As simple notations, then you can think about that for that small delta T horizon, then the probability of zero events and exceeding HC is simply this exponential function here. You can see just simply from here, right? And then basically you have not continuous, you have subsequent events and m minus 1 events that add up to capital T. And is basically, you can even think about very quickly is that this summation is substituted by integrals, right? And from 0 to T, from 0 to T, then for each particular events that occurring at a T, right? And so instead of just one summation of one all the probability functions over these events, then this probability function itself is going to change over time. Then the result is really just an integration solver, right? So then what you really want is to say, what is the likelihood of one or more event tsunamis can generate enough of intense flooding that you need to be concerned with, right? And so it's the one minus this exponential function here. And just like the stationary phase issues, is really in how do you calculate this probabilistic function here, right? Once you know that, you can do this calculation easy. And so in this case, then is how do you integrate this integrals here, and the inside the integrand here again is similar to the stationary phase process. You have to do the prescriptions and for the probabilistic behaviors and in the rupture zone parameters, then you propagate them through the equations, then find out what is the outcomes. Then you have to then somehow decide how do you integrate this whole integrals here. Then you can find out what is the solution here. I will show you a summary of methodology, how do you calculate this. Again, the technical details are quite involved, and I would like you to take some, if you're interested, time to read these papers in those last two papers I mentioned before, then you probably get a much better idea behind it, right? And then actually those methodologies definitely can use some improvement. It's not necessary finished products, then one might be able to come up with much better or accurate methodologies. Here, I would simply show you some of the results, and with the consideration of the sea level rise and perhaps even a sea level rise. Okay, this is the sea level rise. Now, consider sea level rise is a little bit tricky because sea level rise, the trend, of course, it changes depending on what the scenario you propose in terms of human interference of the atmosphere, and so so there are the UN has a study group and they publish different kind of results estimations on different kind of sea level rise depending on the different kind of human activities. And of course, the worst one, is the top one, and then there's a different ones that if you do a lot of reduction of CO2 emissions, and so there's a broad range of the possibilities. Then so we simply take some of the different scenarios and as the input for the sea level rise. That simply means that at a different time, for example, you were talking about 100 years T scenario horizons, you can pick one scenarios and figure out what is sea level rise at a particular, assuming that you can estimate the sea level rise at particular locations or the target region you are interested in, for example, Taiwan, southern part of Taiwan or Hong Kong. And so then you use that different kind of sea level rise as the input for the non-stationary analysis, right? So here just to look at the impact of the results, and you can see that that long dashed line here is the case where you don't even consider sea level rise. In other words, there's a typical analysis for most of us, most of the hazard study are done by most of people actually saying without considering that. And then these different curves are using different scenario, and then you can see also the widespread of the range of the scenarios. Now, again, you just take a one station as example, number 2, somewhere in northern part of Kaohsiung harbors here, and if you think about I think this is 100 years still, and so if you have a inundation at this particular location, this is 1 meters, all right, and so the depends on which scenario talk about, the probability of getting 1 meter is much higher when you consider sea level rise, and now we can be a little more precise about it, and then you can estimate what scenarios you're interested in. You can get a much deeper kind of interpretation or insight of the influence of sea level rise on the inundation depths, right? And apparently it does change quite a bit. Of course, if you impact quite a bit, if you get into the smaller inundation depths criteria, HC, if it's less than 1 meter, you can see the probability increase is much higher, right? That's sort of not surprising, but the differences in the 1 meter type of range is very significant. That's really important. Okay. Now, in the Hong Kong area, I guess it's a similar kind of conclusions. And overall, however, the tsunami inundation high in the Hong Kong area is smaller than in the Kaohsiung areas, right? Now this actually also show you some results with the effects of a tide. Sorry. So for example, this is again is for Hong Kong. I think this is only for Hong Kong. Sorry. So the tides and the sea level rise are considered in this panels, both of them over exposure times of 100 years. And compare with this one is no tide and no sea level rise, and you can see that the difference is quite significant. All right, and so the color code here is probability, right? So this is uh, and really depends on what region you are talking about near the waterfront here, and the difference is rather large, right? Rather large here. So the general idea is that I think is that for a serious consideration of a long-term coastal hazard assessments for this type of coastal hazards, the sea level rise need to be considered more carefully. And for this particular test case, we're looking at it, the sea level rise is a lot more relevant than the tidal case. Right? So this we said that this is all very local because the effects of inundation depends a lot on the bathymetries and landforms effects are significant, and so cannot really make a very general conclusion even for the same regions. Right? Okay, so this is almost like final slides, and it's just a very quick summary in terms of how do we actually calculate this probabilistic function here. And simply what this here is that there's a different way of doing it, and the collocation method is probably a lot more straightforward concept. Is basically your different patches of for the events. Then you simply use the interpolations to calculate the integrants. How do they vary? Then you do the integration through the times, for example. Then there are different way of doing it, and really, well, the technical details really needs a lot of time to digest in more detail. So I refer you to the papers when you have time to take a look at it. Okay, so one thing I must say is that even with this particular consideration, and we simply assume that there's really no dynamic effects in the tides and the sea level rise, right? So basically, so there's no variation in time and space, but only the sea level rise changes only at the particular time you consider the events, but in between the variation is not being considered in dynamically, right? So maybe there is something people can start to think about that. How do we incorporate into that process? And then, of course, there's other source of uncertainties, maybe relevance, and need to be considered when you start to think about this is such a long term, right? And for example, you think about long-term events, you might think about, I don't know how to do exactly, for example, the bathymetry changes, because 100 years, you cannot, I don't think you can say that the bathymetry of the nearshore bathymetry in Hong Kong area will be definitely the same 100 years from now, because we know there's certain infrastructure is being developed, including the artificial islands in those nearshore areas. So if you think about 100 years hazards assessments without considering those kind of a possibility, and really is not that realistic. And at least you need to do something, for example, sensitivity analysis, right? If you don't know how to characterize uncertainties for those parameters, maybe some kind of a sensitivity analysis at least need to be done in this, right? So anyway, we didn't talk about the uncertainties models of sea level rise, and that really getting into too beyond our capability because all the climate changes models have a huge uncertainties. Then how do you incorporate the uncertainty of sea level rise and formulate that in a more theoretical way into our tsunami or other kind of a coastal hazard assessment? That is another level of details. Now, whether that's really necessary or how to do it, that's open questions. And everybody who are interested in this maybe should think about that very seriously. Now, so as I promised to Yunda that I will be in time this time, I think I'm doing well, right? We still have 10 minutes, I think, to open up for questions. And if you have any question on some of the details you want to ask, that's fine. But I have to say, a lot of the technical details that probably cannot be really answered very easily directly, but I will give a shot at it. All right, thank you very much for your time. This is the
Thank you, Prof. Liu, for pretty nice time control. I think we can open 3 questions. So anybody want to do the first one? So I have a small question, which is probably not related too much, because we know that we have several mechanisms to generate a tsunami. So, for example, the landslide tsunami. So, but in the literature, there is quite limited information about the PTHA on the landslide. So, based on your expertise, probably, do you have any comment or any thoughts about how is it possible to do the similar non-stationary PTHA for the landslide tsunami?
You mean landslide?
Yes, yes.
Oh no, that's a very tough one. Yeah, right now the presentation I made here is based on tsunami generated by earthquake. As I said, the earthquake, at least we know a little better of the geography or geophysics of the earthquake, right? We know the major fault zones around the world in the ocean basins, and also we have also a longer time history of the earthquake informations. So in that sense, there's a little better chance to develop this kind of a probabilistic characteristics of the earthquake-generated tsunamis in the source regions. Right. Now, when you come to the tsunami generated by landslide, then it really depends on whether you have equivalent same amount of information for the landslide. Right. The answer is very different situation because a landslide doesn't have occur very often, right? And then also sometimes there's just no data at all to characterize landslide. Most of landslides sometimes are characterized after some field surveys, and you'll find the scars of the landslides. Then you'll sort of estimate what could have been the landslide size and the mechanism. So I know some people have made an attempt to propose some kind of a probabilistic tsunami hazard due to the landslide generated tsunami. But I don't know how good they are. I personally don't have a pretty good idea at this moment to say statistically how do you describe it. I I just feel that there's not enough of information to do it statistically. Maybe you are forced to just think about the worst case scenario type of approach at this moment until one can figure out how do you actually obtain some kind of a meaningful statistics of a landslide.
Okay, thank you. So Yulin raised his hand, so please.
Oh, hi, Professor Liu. Hello.
Hi, how are you?
Hi. Fine. Yeah. Yeah. Oh, yeah. Professor Liu, thanks for your talk. And I have a question about the tie effect in your TPHA assessments, because as I understanding, the tie changes in time and space. So in the tsunami simulation, that we can easily just change the vertical the bathymetry to cover the tie effect. So just curious that are you really included the tie effect changing in time space into the tsunami simulation and calculate to the PTHA?
Okay, so the tie effect, considering tie, well, this could be a tie effect right here in this diagram, right? This sketch here. As you can think about this T, wow, that doesn't make sense. The tie effect has a lot more cycles in there. And but the fact is that in this approach, yes, we can consider the tie effects in there. In fact, some of the results did consider tidal effects in the considerations. Now the I think I think the question in the deterministic way of thinking, I don't know whether that's what you talk about. You're thinking about the deterministic approach. People think about tie effect is just simply thinking about changing the surface water depth according to tidal elevation, right? And
Yes.
then superimpose that to the so-called tsunami inundations.
Yes.
That is that how people do that? Or or another way to do that perhaps is change the tidal water depths according to tides. Then you do the worst case scenario according to the new water depths. But see, the thing is that in those approaches, even in the approach we're doing, that's what we're talking about. We're not even consider the spatial variation of tide in the ocean. In other words, what you by doing those kind of simple-minded thing is simply saying that the whole ocean water depth is going up and down uniformly. Does that make sense?
Mm,
No,
maybe because, yeah.
in other words, take this chart diagram as example. The earthquake occurred here, right? So if you're thinking about, oh, Hong Kong is high tide, right? So the water depth is 1 meter, right? Say high tide is 1 meter. Then you simply add 1 meter to the tsunami inundation depth, original tsunami water depth without a tide, right? Or you can add a 1 meter water depth to the whole region, then runs the tsunami simulations from the source region to the target region. And neither one of them is absolutely correct because the latter situation assumes the tide is going uniformly in the entire basin, right? It's a tidal fluctuation as you have spatial and temporal variations.
Oh,
That kind of linear superposition is simply ignoring that effect.
oh,
Does that make
okay.
sense?
Oh, I see. I think your answer to my question is quite clear. But it comes for about to me that another concern is because tsunami and tide probably the interaction will generate another water level rise. yeah, it's not can be easily super precision to the simulation. Is what I'm
No,
considering about it.
right, right. I
Yeah.
think in that case, I say the tsunami is small enough. You know, which is in the same order of magnitude of tides, for example. There's might be a chances that you're thinking about the nonlinear effects, right?
Yes.
That might play roles. Yes.
Okay. Yeah, I see. Thanks.
So we have another question from Adila.
Okay.
Yes, please.
Hi, do you hear me?
Yes.
Yeah.
Okay.
Yes.
Thank you, Professor, for your nice presentation. I have two short questions, I should say. In your presentation, you were saying that the simulation are being done with ComCAT, and
Yes.
I was wondering if you have done the same testing or the same simulation with other tsunami modeling programs or software. I know, for example, Namidance or the one, that they use in Japan, if they are correlated or if your results are the same for using different modeling
Okay.
software.
Okay, so the quick answer is no, we didn't. The reason being that this analysis here, I think Yulin pointed out correctly that is basically linear modeling.
Mm-hmm.
So it's a linear shallow water version of COMCA or linear shallow water wave equation, basically. So there's no magic to it. I mean, linear shallow water equation, almost any model can do a reasonable job. And so I'm not tied up with any particular model per se. And I think you can do well with any reasonable validated model. You know, you have to validate it. And I think they will all agree with each other pretty well.
Okay, thank you. And the second question is that can this kind of simulation be done in closed sea or it needs to be an open sea? I mean, for example, in the Mediterranean, Europe is a closed sea,
Oh,
but can you do still the
no.
simulation?
Yeah, it doesn't matter. I mean, it's really depending on the boundary condition you specify.
Okay.
Yeah.
Thank you.
And
Thank
in
you very
fact,
much.
if it's totally closed spacing, probably is an easier problem in some sense. Yeah.
Thank you very much.
Okay. So any further comment or question to Prof. Liu? If no, I think we do a very nice time control. I think we should stop here. So last, thanks, Prof. Liu again. And also, just like Professor Liu said, if you have a further question, you can just email him. I think Prof. Liu would be very happy to answer your question about the research. Thank you all for your time and to join this seminar. So hope we can see you again in the future. Thank you.
Thank you. Bye now.
Okay, bye-bye.
Thank you. Bye bye.
Bye.
Bye bye.